Very warm good evening to all the participants and resource person present in this online session. Am I audible?
Yes, sir.
A very warm good evening and welcome to the second day of the 6-day ATAL online FDP on innovative trends in data science and electric mobility, IPR opportunities and challenges. Today we will have two technical sessions. First one being on the topic design of DC-DC converters using LT Spice for EV applications by Dr. S. Shivakumar. And the second session will commence from 7:30 p.m. on digital twin technology for sustainable and smart electric mobility by Dr. Aftab Alam. It is my honor and I am immensely happy to have our resource person, Dr. S. Shivakumar among us for the first session of second day. Dr. S. Shivakumar received his PhD degree from National Institute of Technology, Rourkela. He is currently working as assistant professor in the Department of Electrical and Electronics Engineering at BIT Mesra, Ranchi. His research interests include the analysis and design of high-frequency power conversion circuits, power factor correction circuits, SMPS, electric drives, hybrid electric vehicles, and electric vehicle charging infrastructure. He has published several research papers in reputed journals, particularly in the area of resonant converters. He is also involved in projects related to wireless power charging circuit funded by ANRF. I request our resource person, Dr. S. Shivakumar sir, to please start his session.
Thank you, Deepshikha sir, for warm introduction. So myself, Shivakumar, who is I will share my screen first.
Sir, it is visible. Please unmute your mic, sir.
Okay. So my screen is visible right now, right?
Yes, sir.
So good evening, everyone. Actually, I'm here to present. It's basically a session of. Actually, it should be a lab session where I have to make you how an LT Spice. It is related to LT Spice software, which is basically an analog ICs. It is generally a where the analog circuitry, where you can implement analog circuitry. बीच में ये सब मेरे को क्यों आ रहा है? Okay. So in this session, we will learn how you are going to design basic, generally for EV applications or electric vehicle applications, we require a lot of power electronic converters, right? In which DC-DC converters are also part of it, right? And in this, because what happens generally, we design DC-DC converters on paper, right? What is the power rating? What are the requirements of DC-DC converters? And then we'll go for a simulation aspect. That is, either we'll take power simulation, that is PSIM, or we'll take MATLAB as a tool, as a simulation tool to design or to verify, to validate our design. Now, of that, what happens in general, what we observed over a period of years, like when you are working in this powertronic converters, you tend to see that there is a huge significant difference between what you design in the MATLAB and what you are trying to implement through hardware, right? Suppose if you want to simply design a 100-watt simple a buck converter or any boost converter, in MATLAB, what you will do, you will generally take a switch, simply you will take a inductor, capacitor, whatever the relevant components, and then you few people, like many students, what I saw, they do hit and trial and make a design saying that okay, we got so and so voltage and so current. But when I ask him or her, okay, let us verify it through practicality, then there will be a lot of difference, like 70 to 80% difference will be there, definitely, in general. Now, of that, in order to solve such issues, in order to solve such a basic issue where we can say, okay, we should have a particular software or a tool which is very near to practicality, is what the LT Spice provides, right? So it is not changing. Now it's fine. So can you see the change of slides now?
Yes, sir.
Right. So
Yes, sir, it is
basically,
visible, sir.
yeah, thank you. So basically, the difference, in general, everyone knows what is MATLAB. It is a multi-paradigm programming language where a lot of numeric computing, etc., will be done, and also it will has a Simulink aspect also, where you can have a graphical programming, or you can play some blocks. You can take some blocks and then place it in the Simulink panel, and then go for a simulation. Anyway, I won't take much time in this. Directly, we'll go for, I mean, after half an hour, we'll directly try LT Spice. So I just want to give a brief introduction about MATLAB and LT Spice first. So LT Spice is a high performance spice simulation software which has basically works on analog circuitry. And what are the advantages and disadvantages of this is it clearly provides hardware environment. And I mean, basically depicting the hardware. If you are able to solve, or if you are able to simulate any power tonic converter, either inverter, any DC-DC converter, or some converter in LT Spice, then directly whatever the converter you simulate here, you can directly take those components as a hardware components and then order it and fabricate. You can directly fabricate and see the results which are exactly similar to your LT Spice. Now, what is the basic, I mean, these are the advantages. Now, what are the disadvantages of it? Disadvantage is that, main disadvantage you will first get is that it only validates the analog circuit, that is application ASIC. You know, there are a lot of ICs which we work with, ICs like current controller IC or voltage controller IC, TL494 or UC3813, is tarah ka, I mean, the current controller and all. So those ICs are readily available in this software. So application specific integrated circuits are available in LT Spice. Application specific ICs are directly available in LT Spice.
Information from all other peers also. Inside the smart contract, all the buyers and sellers are.
Okay. Fine. So application specific ICs are directly available in this LT Spice. Now, the disadvantage is that it doesn't, I mean, you have to get certain libraries, import the libraries relevant to motors, because motor is not available in this directly. If you want to design a motor, or if you want to simulate a motor, suppose speed control of DC motor, then DC motor is not available directly. That is one disadvantage. And also it requires lot of space for simulation purpose in order to save those graphical outputs or graphical waveforms. That requires lot of space in the hard disk. That is one disadvantage. So few disadvantages are there, few limitations are there in LT Spice, and there is no digital simulation in this. There is no digital circuitry, like whatever the what programmable devices are not available in this, like microcontroller, etc. Programmable devices are not available. So these are the basic advantages and disadvantages of LT Spice simulator. I'm just skipping this. So there is a basic difference, like in LT Spice simulator, it is open source. Where MATLAB you require, of course, nowadays few people use crack versions, but it is heavier. MATLAB is heavier, and also you require license for that, right? And let's say this LT Spice will occupy very less space, and MATLAB will take lot of space from in the disk, right? So these are the major differences of LT Spice and MATLAB. And as I said, this is mainly used for analog testing, analog circuitry testing only, not for digital circuitry testing. And in MATLAB, the advantage of having MATLAB is that you can simulate many other things. Like, of course, it is totally a big bunch of specialized systems are available already in MATLAB, right? So that is not the thing. But I am talking about particularly about if at all you are choosing powertronic converters, especially the analog converters, because you don't want any microcontroller to control those converters and all, then the best choice is LT Spice. Because you can see many industries, which is Texas, etc., those who are manufacturing the IC oriented converters, etc., they take help of LT Spice only. You can see that LT Spice and also the Plex. There is one more software called Plex. These two softwares. In general, they tend to move towards LT Spice. So this is the same which I already explained. Now coming to now, since I told you this is a kind of lab session, we are going to construct a simple buck converter so that you can get aware of LT Spice in this session. I mean, maybe many of you already know LT Spice. Then please you can ask questions in that, right? So in order to have a buck converter in general, what is the basic construction of buck converter? What is the basic circuit of it has a simple switching device which will have certain internal parasitics, right? And an inductor, a simple capacitor, a load can be a DC motor or any DC load basically, a capacitor, a diode, and a voltage source. So right now we are going to simulate a simple, I mean, I'm just showing basic parameters which are required to simulate the converter right now. So it is a 12-volt DC voltage, and it requires a fast recovery diode, right? Why fast recovery diode? Because we are in general in powertronics, we deal with at least minimum 1 kilohertz switching frequency. We don't go lesser than, I mean, if we can go, but in general, we deal with high switching frequency, we can say, okay, high switching frequency. So that's why we require a fast recovery diode, because what happens in diode, generally it will have charge carriers which are stored in the diode while conducting, I mean, while when it is not conducting. In order to restore those charge carriers, we require fast recovery diode. That is what fast recovery diode means. So this is how it looks like in LT Spice simulation circuit. So where we are taking this is a panel which is shown here how LT Spice looks like. So in order to design a simple buck converter, what is the first parameter required? That is power rating. What is the power rating you are going to design? Let us take 100 watt, right? Then what are the specifications required to design a buck converter? So let us say a power of 100 watt, that is load power is 100 watt. Then what else is required? Let us say 12 volts is the, or you can say like maybe 6 volts. Let us say 6 volt is your load voltage. What will be the output current now? Current will be high, right? How much it will be? Nearly. So DC-DC converter, right? It's very simple. Like, what will be the current? Can anyone just? I mean, those are parties. I'm asking about related to participants.
Participants may unmute their mic and then respond.
Because this is a lab kind of laboratory session.
16.6.
16 point, yeah, nearly 16.5 ampere or 16 approximately. You can say that, right? So what are the just now since the circuit, if you see here, you require a DC. I mean, we have decided the load now. We have designed. I mean, we have decided what is the load requirement. Accordingly, we have to choose the rest of the parameters. Right. So we are going to choose the switch, the inductor. I mean, we are going to design the inductor. We are going to choose switch. We are going to choose the diode, and we are going to design the inductor. Now, if most of you are from, I guess, triple electrical background, what is the relation between input and output in a buck converter? Anyway, I'll just, yeah, there is a duty cycle. Okay, it requires a switch which requires a duty, which is given here, which requires certain pulse. Okay, or the duty cycle, which we call it as a duty cycle. Duty cycle is nothing but the on time divided by the total time, right? And this duty cycle into the voltage, sorry, input voltage, will give you the load voltage, right? Now, let us say the duty cycle is 0.5, right? Then obviously your input voltage will be, of course, it should be already given. It will be 12 volts basically, because 6 volts, if at all you are having the duty cycle of 0.5, then definitely the input voltage will be 12 volts. And what will be your switch? What should see, all these specifications are chosen here. We are going to provide the specifications so that you can design the components in the converter, right? So let us say the switching frequency is around 50 kilohertz or 10 kilo. You can choose 10 kilohertz, 50 kilohertz, or 100 kilohertz also. It depends on your inductor saturation also. You should remember, you should relate with inductor saturation. Okay. In general, we'll take lesser frequency, which is around 50 kilohertz or 10 kilohertz, or you can go for 20 kilohertz also. But in general, for DC-DC converter, it's better to take 50 to 100, even if it is resonant converter, because in resonant converters, we go higher than 100 kilohertz, etc. Right. Now, these are the specifications. Now, let me take one more slide actually. So, since we know output is equal to duty cycle into input voltage, which we already seen in the previous slide. Now, what will be the switch, choice of switch? What should be the MOSFET, or you can say MOSFET? Here we are using MOSFET. We can use IGBT also, which is a power, basically in powertronics. In general, we go for either MOSFET or IGBT for DC-DC converter, or any rectifier, or you can say an inverter. So basically, either you go IGBT or MOSFET. There are many other devices like thyristor, IGCT, etc. We tend to move towards IGBTs for high voltage, high power converters, and MOSFETs for low power converter. Low power in the sense like 500 watt, 1 kilowatt, 2 kilowatt. This is low power here in powertronic converters. Okay. So, can anyone just tell me what will be the switch rating here? Just I am asking, what should be the switch rating as per this specification? In the, I mean, in this buck converter, what should be the switch rating here? Can anyone just, what should be the switch rating according to this converter specifications which we have given? That is 100 watt, 6 volt, 16.5 ampere, or maybe 17 ampere, or less than that. And duty cycle is 0.5, input voltage is 12 volts. What should be the switch rating here?
The 150% of input voltage.
So basically, I think somebody has said 150% of input voltage. So basically, yeah. If you see the converter topology here, the switch is connected to the input voltage source, and whenever there is a conduction, right? So when switch is on, maximum current is flowing in this. So nearly that is output current, load current is flowing into the switch. And when switch is off, the input voltage will be across the switch. So this should be ideally the rating of the converter, right? But since we need to consider the safety factor as to, since V in is equal to 12 volts, yeah, 150% or 200%, we can go for 24 volt and 30 ampere, because I naught is around 16 something. So 30 ampere is fine. So in MOSFET, what are the MOSFET which is shown here? There are 3 terminals of the MOSFET here. That is drain, source, gate. So VDS is, I mean, if you choose the switch rating, that is VDS is 24 volts, and the ID, that is drain current, which is flowing through the switch MOSFET, right? If at all you are taking IGBT, then it will have collector, collector, emitter will be something, the symbol will be something like this. Collector, emitter, and gate. So in that case, this will change. It won't be VDS. It will be VCE and IC. This is a collector current, basically. And if you go for MOSFET, then you require VDS and ID as a rating. So this is the chosen switch. I mean, rating of the switch. Now coming to what is the rating of the diode here? There is one more diode. You can see here. So what should be the rating of the diode here? It's very simple. When diode is conducting, the current will, I mean, obviously the load current will flow into this, right? Through inductor. I mean, the inductor will de-energize through diode only. And when diode is not conducting, obviously there will be input voltage across the diode, right? So the diode rating will also be similar to that, but the question 24 volts, 30 ampere diode. But since the operating frequency of the converter is around 50 kilohertz, so the diode or the converter, since it is operating at 50 kilohertz, it should have fast recovery. There are few types of diodes depending on the there is a term called reverse recovery time, which should be very less, right? Since it is operating at higher switching frequency, right? So depending on this, there are different types of diodes. That is fast recovery. There is ultra fast recovery diode. Schottky diodes, of course, there are Schottky diodes also. So like this, you can choose the diode. I will take one more slide here, last slide. Thereafter we'll go. Then what else? What rest of the components are there? That is inductor. How you are choosing? How you are designing the inductor here? How you are designing the inductor? Simple, which everyone knows here, I guess. In general, we go for simple relation V equal to L di by dt, and for capacitor, this is for inductor. I mean, this is just a regular way of doing. Now, since switch is on here, so maximum current should flow into the inductor here, right? So in general, the input voltage will be when switch is on, L into delta I divided by T on. So if you choose the ripple current as 5% of output current, right? So that is 0.05 into what is the output current here? 16 ampere. 16 divided by. Now you should decide, since it is a 0.5 duty cycle. Duty cycle is equal to 0.5. So what will be the on time? If at all it is 50 kilohertz switching frequency. What will be the on time? Total time कितना होगा? 1/50. So this will be the total, that is 20 microseconds is the total time. So 0.5 will be obviously 10 microseconds. I mean, since duty cycle is 0.5, because generally duty cycle is equal to T on by T. So T on is, I mean, we are calculating T on here. we know T, we know D, since D is given. So T on will be the 10 microseconds. So this will be 10 into 10 to the power of minus 6. And this will be L. This will be 12. Now just calculate the L value from here. How much you will get? Nearly आता है देखो. Can anyone just calculate for the time being? I think it will. Right. Similarly, capacitor also you can just choose. This is I naught equal to C delta V by, I mean, the change in the time, since the capacitor should have maximum charge. Okay, it should accept maximum charge, or it should discharge in less time, basically. So that will be of, I mean, the same T on or T off. You can take T on or T off, the delta T. Basically, delta T यहाँ पे T on or T off, because what happens? Because in general, whenever there is a gate pulse, let us say this is total time, and this time is T on, and this time is T off. So during whatever the capacitor voltage which is there, so in during, I mean, the MOSFET when where it is a buck converter here, so basically it will charge discharge, right? So the capacitor voltage will be something similar to your output voltage, similar to your output voltage. So that's why you can either take T on or T off for this, right? So this is the way how you calculate inductor capacitor in general. Please everyone mute your mics. So just I want to give you the small example how you design a simple 100-watt buck converter. Most of you must be knowing it. I mean, if you have any doubt in this, please ask now, because next we are going to implement it in LT Spice. Participants can ask any doubt in this simple buck converter, where, I mean, few might be already knowing it. If you don't know, please ask now. Then we'll go for LT Spice.
Participants may unmute their mic if they want to ask any doubt.
Till now, like, I mean, I have just given you an example how in general calculation, there are specific calculations separately. For the time being, in practical, in order to suit your practicality, I have given one example, a simple example, how you calculate the components relevant to this buck converter. Boost converter, again, it is different, buck boost converter, but more or less same technique is used. To have a regular way of calculation is this way. But in detailed calculation, if you want, then that is different. You have to go for operational state space analysis, etc. That is separate. But in order to test a particular converter of 100 watt with open loop and all, this is fine. You just can go for a simple inductor capacitor values with this calculation. I mean, there is some logic in this. It's not that hit and trial kind of thing. Okay. So which I have shown you, the logic is in order to test, in order to choose like this, in order to design, you can design like this also. If you have any doubt, please ask now. Not only inductor capacitor, you can choose the powertronic switching devices like this. Considering the safety factor as 2, somebody have given 150% of input, that is fine. That is even 1.5 times also you can take. Because in while sharing the screen, I can't see the name of that. Anyway, so if you have any doubt, please ask now. Just giving you more 1 minute. Because we have to shift to LT Spice now. Yes. Okay. Of course, this is the same thing. So this is how your MATLAB looks like if at all you are going to simulate in MATLAB. And this is the output waveforms of the MATLAB. Like this is the input voltage, this is a simple pulse, and this is the your load voltage or load current. But if you see the major difference in LT Spice and MATLAB here, in general, your in practice, let us take one more slide here. So in practice, the gate pulse which you generate, you will think that in the MATLAB also it is showing like this. The gate pulse. But in reality, in practicality, your gate pulse won't be like this. It will be something like this. Why? Of course, in practical scenario, when you generate the gate pulse, actual gate pulse, I'm not talking about using function generator, which you guys use in the laboratory, or any other generators, that is waveform generators, which are ready-made available. Those might give like this, because this it has got high implicated electronics devices inside, which will smoothen your waveform and make sure that you will get such a pulse waveform which you see in the MATLAB. But in practice, if you generate through certain microcontroller or through certain 555 timer or through certain external source, you won't get exact like this. You will get like this, which is clearly proven from here. You can see here. It is a slant. This is a gate pulse. So LT Spice clearly shows that it is more near soft hardware, and it creates more real hardware environment where it will show, okay, you will get such kind of outputs. But in MATLAB, it is more like ideal case, maximum times. So it is clearly visible that both the mediums produce waveforms as desired. The output values are 2 on point, which might take us some confusion. But the LT Spice have a realistic waveforms. Like in reality, what waveforms you will get? Those waveforms you will find in LT Spice. So there are certain things where how to, I mean, this PPT will be shared, how you choose the components in LT Spice, etc. That I will show in practice now, rather than showing in slides now. Good. I think everyone must have this LT Spice. You can just, it is open source. You can just you can just go to that link. I think Deep Shekhar sir has provided you the link already. You can just go there in analog devices. You just type LT Spice download. You'll get the latest version from here. Okay, you can download that and you can install regular. It is a free of cost, so you can easily download, and it will hardly take 5 minutes, 5 minutes or max 10 minutes if your system is slow. Accordingly, but I am not downloading because I already have downloaded version here. Okay, which I am showing here. You can just go when you download and open the LT Spice, you will get window like this, right? So when you get this like this, the toolbar will be something like this. Okay, and since we know what is the circuit diagram, you just go to the circuit diagram, which you already know. Okay. So it requires a switch, which we already have chosen. The switch should be around 24 volts and 30 ampere switch. It might be available here. So it requires a switch, and it requires an inductor. It requires a capacitor. It requires, first, let us see the voltage source here. So in order to choose the components, you just go here. There is one NAND gate kind of symbol here in the top corner right side. Okay, you just click, or there will be here also in edit option, you may get this one component F2. Can everyone please try to? I mean, many of you must have downloaded the LT Spice version, or you are still downloading. If you are downloaded, then such things should be visible. So just go to the component and then just click voltage, because you require voltage, DC voltage, right? And then just click OK. When you see when you just type voltage here, you just type a voltage here, you can get like this. And place that component in the panel. Just a minute. Hello. Yeah. So you can choose the voltage source. Just again, I will repeat this. So you have certain tools here, and you can also delete this particular item. There is one cut option here. You just click that and just click with your cursor. Sorry, this whatever the mouse and all. And you press escape. It will go, right? So let us say you have as I said, you want the component voltage actually. So let us say voltage. Then again I'm clicking voltage here. Is it visible? It is very small font, I guess. So इसको ज़्यादा बड़ा करने से भी नहीं होगा. You can't get that. Okay, when you type voltage, you'll get voltage like this, which is a selected form, and then press OK, and you'll get like this. And then place at some place. I mean, you can place the component on the panel, and then press escape. That particular component will be leaving. And then when it's showing this this kind of cursor, when it is showing this kind of thing, or the pointing finger with the pointing finger, just press right click. Then, as we know, we are choosing the DC value as 12 volts. See here, this is the difference. Any DC source will have a series resistance, and right now you can't, you don't need to choose. But if you can go to advanced version also, where it is showing either you are going for a sine wave. If you want sine wave, then certain things you have to place. That is amplitude, frequency, kitna 50 hertz. If at all you are providing a sinusoidal source, or it can be anything 60 hertz also. The theta, pi, and what are the number of cycles you want to make it, and also the exponential waveform, right? And piecewise linear waveform, a pulse waveform, etc. So right now we don't require anything. We just require the DC value. So we don't need to go for advanced version. We can just right click. You will get like this. In order to, if at all, I mean, I'm talking about other converters. If at all, since we are doing only for DC-DC converter, here the DC value is relevant. Okay. But if at all you want to go for some other converter like inverter or a rectifier, for rectifier you require a AC source, right? So then you can go to advanced and place sine waveform, right? So right now, since we don't require any AC source or piecewise linear source, the pulse waveform, etc. So you can just place the 12 volt DC source, which we are already. 1 minute. I have chosen none. I have to choose none here. Okay. And then place 12 volts. Right. If you want to move, you can move with this. With this hand, there is a move option also, and drag also. Okay. All these things you can just explore. Right. And spice, if you want to code, then there is a spice directive here. You can code here. Right. Yes. So this is the this is the simple DC source. Now you can go for this. I mean, you have to place this MOSFET of what rating, which we have already chosen. The chosen rating is 24 volt, 30 ampere. So now this is interesting actually. If you click, you just delete this voltage option. You want MOSFET. There are different kinds of MOSFET, that is N-channel MOSFET, P-channel MOSFET, etc. So here, since we generally go for N-channel MOSFET or enhancement mode MOSFET, in order to have low this one, low resistance, or what we say, depletion layer, with low depletion layer, then we can go for this NMOS MOSFET, which is shown with this symbol. Okay, so you can just click. Since we require R, for rotating, you can just click Control R before placing this component. Okay, you can just click Control R like this. It will rotate. Control R. Okay, I'm just writing again here for rotating. For rotating, Control plus R. Of course, while doing it, you will understand automatically. So I'm just again going back to components and NMOS. You can place and just press escape, it will leave. And in order to connect, you can use here the wire. You can just place here, right, like this. And then we require a diode, which is of similar rating. Just place diode first, then I will tell you how to choose the rating here. You can place one diode and then just connect. Now you can just choose the diode here, choose the MOSFET. So this is a general MOSFET, but we require a MOSFET which we have already, like the drain to source voltage should be 24 volts, and the drain current which is flowing into that MOSFET should be, I mean, the rating is 30 ampere, which can withstand those things. So when you click this pick new MOSFET, there is one option here. So this is the beauty of LT-Spice. Because in MATLAB, there is no such option, because here you can see whatever the commercially available MOSFETs or the switching devices, or especially switching MOSFETs, it will show this with manufacturer data sheet, right? That is, who is the Infineon, this one, of course, this is Advanced Powertronics, Alpha and Omega, Siliconics. So you can see, right? And what we require is around 24 volt, right? Nearly, I mean, exactly 24 volt you won't get. 25 volt also you can take, 30 volt also you can take. But it should be, again, the current rating is high. That is, drain current is high here, right? So you can just choose the VDS right now. So from 12 volts it is starting. What I have did, I have clicked on VDS. And for higher rating, VDS of higher rating and gate charge, that is gate change or gate charge is 44 nano. But we require low resistance. That is, or on should be of low resistance. Why? Because we require low conduction loss in the switch, right? So this is of higher voltage, but we require of 24 volts. Let us go down here. So you can see Fairchild, R Ohm, International Direct, IR, all these manufacturing data sheets, data is available in LT-Spice. It's not available in other softwares. So this is one of the great software for implementing or relating to practical implementations. So you can see this is a 25 volts. Then of course after that directly it is going to 30. So any one of this you can choose for the time being, right? So let us choose any Infineon 25 volts having 0.9 this one on resistance, right? So you have chosen BSC 009. Similarly, diodes also. Let us go to just right click. You just right click, you will get like this. Pick new diode. Go to there. And here also, you will, the breakdown voltage and the average current. So what is the rating of this? That is 24 volt and 30 ampere. So you can just click on the breakdown voltage, that is actually, or simply you can say the average conduction current. So it is 30 ampere. But the problem is we will have higher voltage. So you can see, and one more thing, as I already told you, since we are working with high frequency converters, you can see here what is the type. Fast recovery. Let us say type में अगर click करेंगे, if you see the type, if you click the type, you can see fast recovery. LED kind of diodes are also there. Schottky diodes are there. Silicon diodes are there. Zener diodes are there. TVS diodes are like this. So there are many types of diodes which are involved with part number, etc. Because if you go to the vendor, if you say the rating, then he will get confused. You can directly give the part number. You can place the part number with ratings, etc. Directly you can say, I want this kind of diode, and he will just provide you directly. No need of making sure that, okay, I want 20 volts diode or something like that. So directly with part numbers, everything is available in the software. That is the beauty. So let us say I want, what is the ampere rating? 30 ampere, no? Okay, let us say 30 ampere यहाँ पे है. So any one of these you can choose, 30 ampere. Right. I have chosen this Vishay diode. Now one inductor you can place. You can just control while after selecting, you can place control R, and then a capacitor, and then just connect with the wire. And what is the inductor value we got? How much? Anyone can just express? Have anyone calculated? Nobody has calculated. So you can just see, if you calculate, almost you will get around 10 to 15, around 15 microhenry nearly. I'm just choosing that value of 15 microhenry. You can just write that. Or you can just select inductor, or no, I want with part number, etc. Then go to select inductor. Then you can see a lot of manufacturers, that is Coilcraft, Worth Electronics, Murata. Okay, and it is showing 15 microhenry with this peak current, and what is the coil resistance will be there. So you require low resistance value. So you can choose any one, like 0.8, 0.09 is also fine. Okay, like that you can choose. Okay. So this is how the software works actually. And also you can choose the capacitance. Let us say capacitance anyway, you can, 15 micro Henry is the inductor value, and capacitor will be around 50 microfarad. Or any, of course, I didn't calculate here, but you can calculate from this. Nearly around, if you see current here, current is around 16 ampere, and delta, that is 5% of output voltage. The ripple voltage should be, or 1% also is also fine, right? From that, you might get around 4, because current is around 16. On time will be around 10 microseconds. So nearly 470 microfarad. Why? Because you will get around 16. So if you calculate here, 16.5 into the total, the time is 10 to 10 to the power of minus 6 divided by 1% of output voltage. The output voltage is 6. That is 0.01 into 6. You will get the capacitor value from here. So it will be coming around 470 microfarad nearly. It should come like this, or it might be lesser than that. Okay. So right now I'm just on a regular. Let us say 450 microfarad. So then go to select capacitor. Then you can see lot of commercially available capacitors are already there. So you require the electrostatic resistance, lesser electrostatic resistance capacitor. So you can choose any one of this. Does anyone has got any doubt? And choose a load. Okay, after this you require a load here, right? So since it is simple, very simple, of course, 6 volt and 16.5 ampere. So let us say 10 ohm or 5 ohm, or you can have something simple, the load impedance, you can say. What will the load impedance here in general? You can take 2 ohms also, not a issue. You can just go there and click resistance from there and just place here. So let us say 2 ohms, or you can select a resistance also from the available database, right? Now, how to give the pulse here again? So again, you pulse is also a source. So just go the voltage pulse and place it here. Now go to advanced value. Then you can provide a pulse here. So here there are certain parameters like 0. I mean, right, initial value, let us say it is 0, and the on voltage here, that is what is the maximum voltage, we can say V1 and V2. So it will be 12 volts, or 5 volts also is also fine, because the threshold value for that before giving that pulse voltage, here you can see the MOSFET ratings. Okay, because since it is the input voltage is 12 volts here, right? So as per, let us say 12 volts, and this is 0. Let us say time delay, rise time is 0. On T on is D into Ts. You have to give like this, or you can give 10 microseconds also, since we know the but I want it to be customized. And this one will be your T S. So I have to first connect this. Actually, it should be connected to ground, but gate to source, in general, we do it for gate to source. In general, it should be a gate to source voltage. It's not gate to ground, actually. And then provide twenty microseconds. So you are basically initiating, or you are assigning the TS value with 20 microseconds. You have to write a spice directive here. Okay, that is what I have done. I have just gone there and clicked a spice directive and just write down dot param. Dot param gives you the parameter. Okay, duty cycle as 0.5, or you can write at a time also, not an issue. And then you have to run this in transient for 5 milliseconds. ये वो नहीं है. Oh, sorry. ठीक. So till now, if anyone has got any doubt, please ask. Because now we have completed how to design a simple, very simple, a buck converter of 100 watt in a LT spice. Because you must, I mean, here it's something like equivalent to your getting aware of LT spice here. If anyone knows already, then please ask. If you have any doubt, participants, please ask some question related to this, if you have any doubt in this. So it is giving certain errors. It doesn't have any ground. I have not placed a C value. So I am placing ground here. So you can see. And in order to check the voltage, we don't require any voltage measurement or current measurement to place in between. You can just provide a cursor here, and across voltage, like if at all you want to check the voltage across the inductor, then you can just place one point here, click, and then the other point, holding the cursor, you can just press here. You can get the inductor voltage like this, right? And if you want the voltage, the load voltage, of course, you can add. Then go to the panel, add plot pane. You can just place that, and then again coming back to that whatever the converter you have already designed, place one cursor on the top node. I mean across the one node. Press hold, and then the other node you just release. You'll get this is the converter. Yeah. So you are getting almost 6 volts, 6.3 volts, which is right, because 0.5 duty cycle and you are giving input as what we say, input as 12 volts and 0.5 is the duty cycle. So you are getting exactly. Now let us say you want this one gate to source voltage. So I'm placing the node at one node at gate and then other node at source. Okay. Let us add one plot pane and then just click and just drag that particular nodes. So this is the gate to source voltage. So you can see here, it is not the straight, it is slant one, and almost 6.3 volts. And here the this is the inductor voltage, of course, 6 volts exactly you are getting. So ideally you are getting correct. I mean, whatever the practicality you require, that is getting fetched in the LT Spice, where the results itself are showing, I mean, results itself depict the hardware reality in this software. So if you have any doubt, please ask now. If you want current, for example, you just provide your cursor on that particular component and then press. You will get the current here. See, the inductor current is this one. Or you can just, if you want to see separately, you just add plot pane. You just click on that particular parameter and drag it. You will get the current. See, you can see clearly. Whenever what we say, switch is off, your current is decreasing. And whenever switch is on, your current is increasing from 1.2 to 3.2 ampere nearly. So ripple is very less. This is 5% of output current, which you already chosen. So everything is getting matched here, and it is very near to where if you solder this with the same component values, directly purchase this. No need of again testing. I mean, what happens like generally the students do hit and trials. They will just go, 20 volt, 1 ampere. Oh, okay. They will go to vendor, ask the vendor, I want 20 volt, 1 ampere. Then he will, the vendors, of course, they don't know much of the component specifications. They will give some fake component or some relevant component which is equivalent to that. But when you come to lab again and fabricate it on the PCB, you won't get the exact results. This is for sure. Now here, you can, there is no, you don't need to, what we say, provide holes to your pockets unnecessarily. Okay, you can just come to LT Spice. I mean, I'm talking about powertronic converters. I'm not talking about like if you want a big grid system or any other. Those components, it will take, I mean, there are certain libraries which you have to again import to simulate those like high embedded components or high what we say grid elements or motors, etc. Okay, so even programmable devices, etc. But here we will have some ICs also. Analog ICs are also readily available, right? So if you go for analog powertronic converters, then this is the best software to deliver, and that is relevant to your electric vehicle applications. Because in electric vehicle, most of the converters are bidirectional converters, inverters, rectifiers, these buck converter, boost converter, resonant converters. All these can be readily we can simulate in LT Spice, that too relevant to practicality. Not like in a space where you can just have a visualization. Okay, MATLAB may run, it is running in MATLAB, it will run in, it is equivalent to your practical thing. No, that is not true. But in LT Spice, it is it is depicting totally the hardware, which we have proven just now. Even if you simulate inverter, you will get similar things. The only disadvantage here is we can't use any microcontroller, anything, any programmable device directly in the LT Spice. So please ask any doubt. If you have any doubts, please ask now.
Sir, am I audible?
Yes, sir. Deep sir, you are audible.
Sir, could you please repeat the method of measuring the current?
Right. So I'm again going. Suppose previously I have uh, measured this inductor current. Let us say I want to measure the MOSFET current, right? So just this is a cursor, right? You just place your cursor on the component like this, okay? Or you can place the cursor like this. Suppose if you want a capacitor current, so the symbol will be like this, okay? If you want to place, if you want to measure the current of load, the symbol will be like this. You can just place exactly at the center of that component, this component, or here also you can see. Of course, in MOSFET it is not showing, but see in the voltage source you can see.
Yes, sir.
Right. So, but here of course the symbol is quite different in the switching device, in the MOSFET. So like this you can place. Let us say diode current if you want to measure. You are just pressing. Press click. I mean, if you are clicking, you can see here. You can see the diode ID1. Okay.
Okay.
Then
sir.
just
Yes.
just provide. So this is the diode current. You can see
Just
whenever the
simply
inductor
place
current is
the
increasing.
cursor. Simply place the cursor and then just click.
Yes, whenever this arrow symbol you are getting now,
Okay.
you are getting an arrow symbol here. So just
Mhm.
no need of separate ammeter, voltmeters in the system. So directly you can see, even in the here also you can analyze, like there are many plot settings are there, many you can just visible traces. There are many FFT. Yeah.
Yes, sir.
So FFT is also there. So many analytical tools are also there where you can analyze the waveforms.
Yes, sir. Like in MATLAB, we do FFT for that THD
Exactly.
analysis.
Exactly. So there are many other tools are also there where you can explore, and even you can, I mean, you can copy this and you can change the, I mean, font, etc. Anyway, that is how you present the results in the paper. That is different aspect. So this is how the LTSpice software help us have a cushion, provide a cushion that bridging the gap between hardware and software, which is very near. I mean, if you able to simulate a relevant converter, a converter in LTSpice, then automatically if you directly go and place these components and fabricate these components onto a system, I mean onto a PCB, directly you will whatever the results you are getting in here, you will get the same result here also. I'm talking about making a particular system from scratch. ऐसा नहीं कि जाके directly you are purchasing a particular converter from the market and sir I can get all like this. Then that will as I told you, it will provide holes to your pockets. So anyone can ask any doubts now.
Sir,
Yes.
sir, I have a question. So,
Yes.
can we integrate Python with this LT Spice? Because sometimes it happens we want to
Actually, just now I expressed there is no such option actually with Python, because programmable devices are not in the analog circuits. You can do analog ICs, etc.
Okay, sir. Thank you, sir.
Programmable devices are not in this system, in the LTSpice systems.
Okay. Thank you, sir.
Hello.
Yes, sir. Yes, sir.
Sir, how PSpice is different from this LTSpice?
Sir, PSpice you have to code with certain nodes and etc. Okay, you have to provide. I mean, as far as I know, but LTSpice is more practical compared to PSpice.
So can I use this
is
LTSpice software for drawing the analog electronic circuits?
Yes, definitely. If you are going for analog electronics, I recommend you please go and simulate those whatever the analog electronic circuitry is there. in this LT Spice, then it will be helpful for, I mean, you can automatically see the difference. You try with simple electronic circuitry first.
Okay, sir.
Then
Okay.
you will
Thank you.
understand what is the difference.
Yes. Okay, sir. Thank you.
If
Excuse me,
anyone is
sir.
working with analog circuitry, please go for an LT Spice without any doubt. Yes, sir.
Okay. Sir, is it possible to means interface this particular thing with some other softwares like importing its result or exporting its result to into some other software? Like
Right now,
is it it may be interfaced, maybe it may be interfaced with MATLAB or something like that.
right now there is no, as far as I know, there is no such provision
Okay.
of importing certain library. But there are, LT Spice is a separate software where you can import certain libraries within itself. Suppose if you want to, as I said before also, that motor you can't directly, it is not available in the components level. But there are certain libraries which you can import from the analog devices. There is one website, the company which is providing.
Yes,
So
sir.
from there you can import certain libraries of motor or some parts which are not available right away in this. So those things you can do, but as far as, and also the data you can take from whatever the waveform data is there, you can take from this. But I don't think there is any interfacing kind of like PSIM, MATLAB, there is interfacing. As far as I know, PSIM is separate software, power simulation. Here we can import co-simulation kind of technique is there for PSIM and MATLAB. But for LT Spice, I mean, I don't know what are the latest update. Maybe in a week or two, we may get some interfacing of MATLAB or LT Spice. Right now,
Okay.
as far as my knowledge is concerned, I don't have this information about interfacing MATLAB and LT Spice.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Good evening, sir. Sir, is there any arrangement for grid connected inverter or
Great.
any components?
Inverter you can simulate, and equivalent to your practical conditions you can simulate. Even grid connection also you can do, not a issue. Grid connection is also an analog one. There is no program or some sort of thing. You can do it. Grid connecting inverter in this. Whenever some programming kind of things comes, then a programmable device kind of component comes into picture, then it will reject because it has only analog circuitry.
Okay, sir. Okay, sir. Thank you.
Thank you. Thank you.
So, sir, related to that question only, grid connected.
Yes.
Means in that case, the grid can be represented using a source only.
Yes.
Three-phase source
That
or
is
a
what.
single phase
Three-phase
AC
source
that's
only.
all.
Yes, you are right.
Yes. Okay.
Three-phase source only. You are right. Actually, this, if at all there is a live session, then this will be more helpful. In my online, I don't think most of the people must have gone downloaded and gone hands-on experience kind of thing must not be visible here.
A live lab session would have been more beneficial.
More beneficial as far as
Offline.
I understood. Offline.
Yes.
Because here in online, we don't know who is doing, who is not doing.
Participants, the session is still open for questions. If anybody is
Yes.
interested, if you have any doubts, you can clear them now.
Good evening, sir.
Yes, good evening.
Sir, my question is that is there any technique to select any component in LTS Spice, or we can like you told that there is some specification and the manufacturers are having some
Provide
their
the data sheets.
specification.
Yes.
Yes, sir. So can we modify them as per our according to our need?
Yes, you can modify. Very good question. Yes, you can modify and customize. You can do that. There is an option in that. You are right. Good. You can modify according to your convenience. That option is there. Yeah, that library can be changed. There is a process for that. It will take more half an hour to explain that. But you can just go to that library and then modify that library according to your whatever relevant parameters you require to modify. You can do that. Good question. Yes, anyone? I think somebody.
So I think there are no more questions, sir.
Okay, thank you.
So, so I think we can wind up this session.
Yeah, thank you. Thank you for giving me such opportunity to deliver a to deliver this lecture. Actually, this should be as I told you before, a practical session. Honestly,
Yes, sir.
but in this we can deliver like this only. Okay, thank you.
Thank you, sir, for a wonderful session with practical applications of the LT Spice software for designing DC-DC converter.
Yes.
Starting with the basics, taking some minor calculations, how we reach to the specifications to be set for a particular component, everything was detailed. Thank you for the session, sir, and
Thank
we
you.
will look
Thank you.
forward for future collaborations in future sessions also.
Sure. If there is any
you
live
very much, sir.
workshop or live session, then surely it will be. I will be readily available.
Sure, sir. Thank you,
Thank-
sir.
thank
Thank you very much.
Thank you very much, sir. Very good session.
Thank you. Thank you.
Thank you, sir.
Pramod. Thank you, Piyush ji.
So
Thank you.
just like yesterday's practice, we will try to maintain the practice in this session. I request all the participants to please switch on their cameras so that we can take a screenshot. We can take a snapshot along with our resource person. Just a few seconds more. Thank you, sir. Thank you, participants, for switching on the camera. Thank you very much, sir, for a
Thank you.
wonderful session. Thank you, sir. Thank you very much.
Thank you, sir.
Thank you. Thank you,
Thank you
Nitish
very much.
Bharadwaj.
Thank you, sir.
Thank you, sir.
So with this, we come to the first session of day 2 of our 6-day online FDP. We have among us our next resource person, Dr. Aftab Alam, who will be talking on the topic of digital twin technology for sustainable and smart electric mobility. Dr. Aftab Alam received the BTech degree in Electrical Engineering from West Bengal University of Technology in 2009 and the ME degree in Electrical Engineering with specialization in Power Electronics from Birla Institute of Technology, Mesra, Ranchi, India in 2012. He has earned his PhD degree in the field of electromagnetic compatibility in power electronic converters from the Department of Electrical Engineering, Birla Institute of Technology, Mesra. His area of research includes the development of high-performance drives and electromagnetic interference in semiconductor-based power switching devices, IoT-based applications in energy management, and wireless power transfer. He has published in many journals of repute such as IEEE, Spinger, and IndaScience. He has developed hardware design of IoT-based energy management systems using cloud computing platforms. Additionally, he has also developed a novel battery management system for which patents have already been filed. His research area includes the development of an embedded system for general purpose AI in the field of automatic navigation of electric vehicles and aerial vehicles. He is also developing an AI-based cybersecurity system against cyber attacks on the grid-connected microgrid. Currently, he is working on the development of a 50 kilowatt wireless power transfer system, which is tolerant to misalignment and thermal drift. He is also developing an electromagnetic interference compatible filter and shielding mechanism. And he has earlier developed a 5 kilowatt wireless power transfer system. I request Dr. Aftab Alam sir to please start with his session.
Am I audible?
Yes, sir.
Okay, so good evening,
Welcome, sir.
all the participants, and yeah, thank you. Good evening, all the participants and respected faculties. Just let me share my screen. Is my screen visible to all of you?
Yes, sir.
Yes, sir, it is visible, sir.
Yeah, okay. Okay, I welcome all of you to this discussion on digital twin technology for sustainable and smart electric mobility. So I will be presenting this topic in the Indian context. Okay, the technologies which we are developing or being developed across the India, and what is its international status, and how we are doing in comparison to that one. So and how digital twin can actually help us to improve the situation. So at first, I will tell you that one thing, I would like to break one myth here, that many of us think that electric vehicle is now coming because of the power electronics has emerged, or semiconductor devices, high power semiconductor devices has emerged, or government is pushing for the climate change. That is definitely not totally wrong, but even before that, even in late 1930s, actually the electric vehicles were being utilized in some places like Nottingham in the UK. Okay. However, those were not very efficient. That's another thing. But down the line, when the Henry Ford came with his IC engine and the gasoline became cheaper, the entire market of the electric vehicle was totally gone. And that was the reason that what started in 1900s, it stopped, and now we are again back to the same place. The reason we are again back to the same place because the climate has climate is posing a serious threat to all of us, and all the governments around the globe are placing a lot of very ambitious targets for carbon emissions, reducing the carbon emissions, and a future towards net zero emission. Okay, so therefore we will also start with what our government has set, the targets. I will explain about the power requirements of different kinds of electric vehicles, and charging infrastructures, components of electric vehicles, and the main objective probably of this entire workshop is sustainability. How the EV can be sustainable and what are the challenges in that sustainability. So I will discuss my talk in first 3 sections. What are the challenges in EV mobility, okay, and how to make it in sustainable, and what are the solutions, and how a digital twin can actually emerge as a very potential solution to all the problems. So at first I will start with the challenges in the EV mobility. So our government of India has also set very lofty goals of attaining net zero emissions by 2020. Okay, already at the CEM, there's a campaign EV30 at the rate 30. That means by 2030, they want to make 30% of the private cars and 40% of the buses and 70% of the commercial cars, 80% of the wheelers and 3-wheelers totally electric. Okay. That is CEM stands for Clean Energy Ministerial. It's basically global organization formed by UNO. Headquarters are in France, but actually they operate all over the world. And one major part of our Indian transport systems are our trucks. And as it's going to come that the trucks are actually one very major role, are going to play a very major role in reducing the carbon emission if we can make them electric. So what kind of powers we are talking about? Let us have a look on this power requirements required by different vehicles. So e-rickshaws, which is e-rickshaws and electric scooty, which still forms more than 60% of the entire EV sector in India. Okay, and electric cars. So electric rickshaw and electric scooty, they usually have a power like 2 kilowatt and 10 kilowatt. If you 10 kilowatt, I mean to say, if you look at some latest models of ATAL, they have these 10 kilowatt models which are coming. E-rickshaws are usually between 2 kilowatt and 3 kilowatt. That is there. Electric cars now, e-Nexon and Hyundai Ioniq, Mahindra BXEV. These models will range somewhere between 150 kilowatt power they will be requiring. The power, by that power I mean to say the power required by the electric wheel, by the electric motors. In the electric vehicle, the traction is given by the electric motors only. Okay, so these are the requirements of the power by the motors. And if I assume that the efficiency starting from the battery to the entire transmission and to the vehicle, it's about 90%, which is not very unreasonable because usually there will be not many losses as compared to the mechanical transmission where you need gearbox and differentials. All of that will be gone in the electric vehicle. So the power efficiency starting from the battery to the powertrain and to the motors, electric motors, will be 90%. So if we only talk about the electric motor rating, that is a good estimate how much power we are going to need. Then eVTOL is a concept where electrical vertical takeoff landing vehicles are also going to come. In China and in the few places in the Germany, they have already started this kind of services. This is basically kind of a vertical takeoff landing vehicle, much like helicopter. It takes off and it drops you at some place, maybe at your office at somewhere. Okay, so the power requirement by eVTOL is basically a 250 kilowatt. Electric buses. The electric buses are going to like some models of Ashok Leyland and other models usually need 350 kilowatt hour. 350 kilowatt power. Now 350 kilowatt power is a huge amount of the power. Considering the amount of buses which are going to run at least in next 5 or 10 years. The electric trucks are going to require 500 kilowatt of the power. Okay. Yeah. So if you combine electric buses and electric trucks, okay, they almost and let us say 1,000 vehicles, 1,000 electric cars. If you combine this amount of the power, even if you look at, let us say just the electric trucks. If 100 electric trucks are running, and 500 kilowatt power they are consuming each truck. So it's about 5 megawatt. If I 500 kilowatt and 1000, right? So about 5 megawatt power is required to run the electric trucks, and all of this power are going to come from the battery. So definitely battery is going to be very important, play a very important role, and their sustainability is going to be the critical in deciding whether the electric mobility is going to be sustainable or not. Now down the line also, the electric planes are also coming. Okay, few people in some universities, I know some of the colleagues, they are designing the electric planes also. The power requirement is breaking the roof in the case of the electric plane. It's about 500 kilowatt per electric plane. Okay, so one electric, if you talk about 10 electric planes, they are already like a power station on the fly. Okay, so we are looking at a huge amount of power requirements, motor ratings. It will be supplied by the battery. So if they fail, if the motor fails, or if the battery fails, or if the power converter which is going to run them, they fail, the dream of the sustainable EV will never be realized. Okay, and how they can fail actually. So that is what we are going to look. Before that, let us have a quick look, which is a very basic information regarding different types of battery electric vehicle. I'm expecting that if some of the audience may be new to the field, in that case, basically you can divide it in the 4 categories: battery electric vehicles, where the entire traction is given by the battery; fuel cell electric vehicles, where the traction is given by partly by the fuel cell. That means the fuel cell is converted to electrical energy, and then the entire thing is run by the electrical energy only. In HEV, the traction is given by IC engine and the motor both, but there is a catch. The battery which is going to power HEVs, these are very small powered batteries. Whatever has been realized, like some models in the Reva and all. So the batteries are only to give a start. Okay, and they are very small, of very small capacity. So HEVs are not going to solve the problem of the climates. But plug-in hybrid electric vehicle is an entirely different story, in which the traction is given by the IC engine and by the electric motor in both cases. And both of them are going to give a substantial amount of the power, but their prices are going to be very high. Let us have a look. Whenever we talk about sustainability in electric mobility, the economics has to be viable. The customer must get the value for his money. So he will require the range of the vehicle, definitely charging time. None of us will like to stand for hours in a charging station. Okay, and then cost, definitely. We also want it to be very less costly. We have this Sasta Sundar and Tekau thing in our India. So it needs to be like that. So range, if you see, fuel cell electric vehicle, the highest range you are getting out of HEV. That is true. Why? Because it is being powered from the battery also and from the gasoline also, both. So definitely they are going to have the highest range. Okay, and the plug-in hybrid electric vehicle are also having quite a large range as compared to the BEV. So battery electric vehicle is having lesser amount of the range as compared to the HEV or PHEV. Fuel cell electric vehicles also are having a higher range. So what I want to I want to make a point here, that out of all these 3 categories, if you see the battery electric vehicle is having the least amount of the range, then why we are going for, then why did the push around the industry and by the government for the battery electric vehicle? That part will become clear partly in the charge time comparison. In the HEV, if you see, they are self-chargeable. So, so there's not much amount of the time required to charge the hybrid electric vehicle. And then a plug-in hybrid electric vehicle also needs some charging up to 6 hours. In HEV, the motor, the part of the means the generator, basically the motor runs a generator, and that charges the battery in the HEV. So there's no need of extra charging. Okay, that's why it's self-chargeable. Fuel cell, you just need to replace the hydrogen tank. Hydrogen infrastructure is a big challenge, definitely. Okay, but if you come to the economics, the cost of this one. Okay, so you look at the fuel cell electric vehicle, it is highly costly. Okay, 80 lakhs rupees. If you go to the plug-in hybrid electric vehicle, they are also highly costly. But if you come to the HEV and battery electric vehicle, their costs are comparative as compared to the fuel cell electric vehicle and plug-in hybrid electric vehicle. Okay, but as we are going for the completely climate push, government wants to reduce the HEV also. They don't want to tolerate any gasoline-based transportation. So that is why only solution now is the battery electric vehicle. Coming to this part here, the major components of any electric vehicle are basically the battery management system, the motor design and electric drive systems, and the electric vehicle charging infrastructure. What are the reasons that these can fail, these components can fail, and how we can make them sustainable? That is what my first part of the talk is there. Okay. So first of all, coming to the motor part, if you see, either we are going to use the BLDC motor or the PMSO motor. Definitely, induction motor is not a solution, not a viable solution because of its weight and less power density. So if you go for the PMSM, the problem is that there's a permanent magnet which are made of the rare earth elements, and with the time they tend to demagnetize. Once they get some sort of demagnetization, the amount of torque which you are supposed to get, that will also decrease. Okay, and if that happens, there will be multiple types of failures, mechanical failures and electrical failures, all that will start to appear. So, and even if you don't consider this as a big issue, definitely the mining of rare earth elements has become a major issue of conflict in the geopolitical drama. Okay, China has a complete monopoly over the rare earth elements. So somewhere we have to find a solution which is less dependent on the rare earth elements. Otherwise, the motors will not be a sustainable part of the EV. So what are the alternative magnet materials? Okay, so alternative magnet materials are ferrite based, which is basically metal doped with carbon, magnesium, zinc. Okay, iron doped with carbon, magnesium, and zinc, and under certain temperature and pressure, they form the ferrite core. And if we magnetize this ferrite, the tendency of demagnetization in the ferrite becomes very less as compared to the rare earth elements. The issue with this one is that the size is very large. Okay, so not very large. I mean, comparative to rare earth element based magnets, it is large. So that is one of the. So if we go for ferrite based materials, then SRM motors or PMSM motors, they will increase in the size, but at least our dependency on the rare earth elements will be gone. We will have a magnet free drive. Okay, so again, to make it the fault tolerant, the windings in the motors has to be fault tolerant. So because to make this fault tolerant, people are going for this hairpin kind of winding, which is being shown here in the image. Okay, just a minute. Let me have this. Okay, so at the higher speed, the motors windings tend to fail sometimes because of mechanical failure. But this hairpin kind of structure is going to be more reliable. So as compared to the conventional winding. Okay, motors are going to be the major horsepower of the electric vehicle. So no failures we can accept there. And neither there should be failure in the motor winding, nor there should be any failure in the inverter. And if it is, what is the way forward for that one? You can see that compound annual growth rate of the motors are supposed to, till now it's like $15.48 billion up to 2030. This is going to go up. Now this will go up only if we have the sustainable drive, if we have sustainable motor designs, cheap and less reliant on the rare earth elements. Okay. Currently, whatever, if you have seen, if you just Google out some images of electric drives for the motors, electric vehicles, we find out that the drive systems are outside the motor. Means there's a box drives, electrical drives. It can be for PMSM, BLDC, whatever. From that box, there are some harness wires are coming, which are connected to the motor. So these two are different entities, one motor, one drives. Okay. But now the concept of the integrated drives are also coming, in which the drives will be basically mounted at the exterior of the motor, or at the front, or at the front side or the rear side of the motor. So the entire IGBTs, reverse recovery diodes, everything is basically mounted here on this at the outer periphery. Okay, this gives us a very robust design for the drive system. Okay, now as I was telling you that what are the challenges, like here in some images we are showing it, some of the windings has been burned out. Okay, now if some of the windings are burning out, what is going to change in the motor? Let us say only 4 turns out of 100 turns have burned. Will the motor stop? Will you come to know about it? No, never. If only 3, 4 or 10 or some lesser amount of the windings have become shorted, still your motor will work. The motor will rotate. Okay, but that's an indicator that now some fault is coming, and you sooner or later in the entire windings of that particular phase are going to be burnt out. Okay, can we stop this before happening? Like, can I come to know that only 3 to 4 windings have been burnt out, so some sort of repairing is required? Because unless you open the motor in the service station, no one can tell you that actually it requires repairing. So we need a mechanism to know these kind of events beforehand, means when they are on the progress. Okay, when the damage has not overtaken the operation of the vehicle, but they are on the progress, and before that we need to do some diagnostics and prevent them from further escalation if possible, and also suggest repair and maintenance. So this, I will come to this part in the digital twin part, how actually we can actually, if you see, whenever you talk about these windings, if they are going to be shorted some part of this, let us say, then their inductance will decrease, their resistance will decrease. Okay, but if you measure the decrement in the resistance and the inductance will not be immediate. It will take some time to for that to happen. Okay, and that can be captured by doing some sort of signature analysis on the motor, on the windings. So, so for that, I need to have the complete. I need to observe the parameters, all the parameters of all the windings in the motor, and if there is some certain drift in those parameter values, that is an indicator that the fault is going to occur. How do we do that? I cannot go with the multimeters every time, or impedance analyzers, open my motors from the car and do the testing to find out what's happening. That's not practical solution, and not for consumer application. Definitely it's not going to happen. Okay, so and again, another major fault is these IGBTs. If the IGBTs get shorted, what we can do about this one? Other thing is, if let us say, as for example, there is a lot of dg by dt stress coming on IGBT, and slowly forward voltage drop of that particular IGBT is going down. Okay, if someone can have an idea or measure this part without actually opening the drive, definitely that forward voltage drop is going down. That can be an indicator that this IGBT is going to be burnt in very soon. So if we can estimate these parameters using some sort of mechanism, which is turn out to be a digital twin, which is going to be turn out to be a digital twin, then we can have a sustainable solution. Okay. So in a digital twin, basically, there will be a high fidelity mathematical model in your digital twin. Okay. So and that model will get its own means all the data. So I have an entire talk over that digital twin. So that's going to come. Here it's just that all these, you can see this high fidelity model. Okay, so there is an actual car in the physical space. The data will come from that physical space. It will be put in the mathematical model of the car or of the converter or of the motor or all of them together. Whatever it is, depending on how much depth we want to go. Okay, if someone is just interested in the motor health, you can put a mathematical model of the motor, or if someone wants to launch a very reliable product, then you have to put the mathematical model of converters, inverters, batteries, and then the mechanical chassis of the electric vehicle. And in that, the data, the measurement data, voltage, current, vibration, will go into that model. Okay, and that model will compute, and through cyber physical interface, the results will go to the digital, in the cyberspace, and there will be some sort of parameter estimation algorithm, which I am going to explain after some time. Okay, and then you can visualize. So this data, this structure which I have taken, this is an IEEE standard. It's a P288.3 standard. So they have defined anything will be called a digital twin, or the digital twin will have at least these 4 spaces: high fidelity model and an interface, cyber physical interface. Okay, this some sort of estimation or simulation you can have, and then monitoring of the parasitic elements, or this is basically application. I have written here monitoring of parasitic elements. Someone can do something else also. Okay, so I will also show you the structure which is suggested by IEEE P288.3. Again, I was talking about the switching stresses. You can totally remove the switching stresses if we go for the zero voltage switching and zero current switching based mechanism. So that will again improve the efficiency and the life cycle of the converter, which is ZVS and ZCS is definitely going to play a crucial role in maintaining the sustainability of the electric vehicle. So some of the ZVS, ZCS has been developed in our lab. Just now, the previous speaker, Dr. Shiva Kumar, was talking with you about the PSpice. So he and his team has developed this short switching based power converter. They have plans to scale up and come up for the higher voltages also. So I just put here for your interest. Another major challenge in the sustainability of electric mobility is your charging infrastructure. Okay, these are multiple standards of the charging infrastructure. So there are multiple pin diagrams, multiple sockets. Okay, and the standards also I have mentioned here. These are all standards. Now, one challenge is that just imagine, and how these standards have been given. They are given according to their power delivery capacity. Okay, some low powers are 10 kilowatt, 15 kilowatt. Medium power, you can say 50 kilowatt to 100 kilowatt. High voltage levels are, we can have a separate discussion over the entire Bharat AC 001, Bharat DC 001, fast chargers and slow chargers. But now imagine a scenario where a car is being charged with, let us say, CHAdeMO DC charger. It is having a power delivery capacity of 200 kilowatt. But your car only needs 50 kilowatt, for example, or 30 kilowatt. Okay, and after that, it is charging at a charging station. There comes an electric bus which needs to charge at 100 kilowatt charging power. But it will have to wait, right? Because your car is charging. Now that is, your car only needs 30 kilowatt. But that power converter, which is inside the kiosk, the charging kiosk is there, where the gauntlets will be there. It is capable of giving you 200 kilowatt. Okay, but unnecessarily that electric bus is waiting because a 30 kilowatt car is charging. Okay, and remember the charging time has to be reduced. Already we are struggling to reduce it anything below 15 minutes. Although the charging time of 15 minutes has been claimed by multiple manufacturers. I know if you see like Tata Powers, and they are charging, they are saying, they're claiming it, but definitely that is going to deteriorate the battery life. And even after that, some vehicle has to wait, that's going to add additional time, which can be a major deterrent for faster adoption of the electric vehicle. No one would like electric vehicle to adopt the electric vehicle in this particular case. So what we can do, this kind of solution, that to keep the power converter in between and all other gauntlets, like let us say 30 kilowatt, 100 kilowatt, 200 kilowatt chargers at separate distributed places. So now a 30 kilowatt car can charge here, and a 100 kilowatt bus can also get charged. So these kind of solutions are also being discussed. The moment when you are doing this, okay, the reliability will also come into the play, because it has to come through this cables. The cable fault should not occur. And again, how do we solve the, and the cable will be charging cars day and night. Can we have some sort of method to detect before the cable fault can occur? Okay. And if this charging station is developed by Tata Motors and there comes a car developed by Mahindra, will they have compatibility? What kind of solutions we can have for that one? So this problem is actually interoperability, where multiple charge point operators are there, because charging has been declared by government as a de-licensed activity. So if you have money, you can also tomorrow open a charging station. Okay. But what software you will implement on your charging station? What whether your power converters will be able to communicate with the cars made by Mahindra, by Tata? Are they having a common platform? So these are very big questions and very big challenges. So this can be basically answered as you need to have interoperability. EVs should be able to charge at electric vehicle service stations or by electric vehicle service equipments made by different charge operators, by different vendors. Okay. And your chargers should be able to operate with different networks. So I will explain this part here. This is better. Okay, so let us say a car comes here at one of the charging point operators. It is not available. So in order to go to the next charging point operator, this EVSE needs to be compatible with the electric vehicle. Okay, so this is one of the big challenges, because how do we bring Mahindras, Tatas, Hyundais on a common platform where they will agree that I will use this particular protocol, and with that particular protocol, everyone will be happy and they will be able to their equipment. I mean, by that equipment, I mean the battery management system and the power converters. They should be compatible with each other. Okay, so that is one of the interoperability, EV to EVSE interoperability. Then next one is your charging point to CMS interoperability. The charging management software definitely will be developed by a software company. Okay, and if I am a charging point operator, let us say I have set up an installation, I have bought it from Delta Electronics. Tomorrow, if I get at a lower price, I would like to buy it from some different vendor. And all of these charging equipment needs to be communicating with a charging management software. Okay, CMS. So they also needs to be interoperable. So this is Government of India has given a white paper publication in which these three interoperability has been identified. Without this, the dream of sustainable electric mobility will just be a dream. It will not be realized. And then all the CMSs, all these charging point operators, or charging point operators means their software needs to be compatible with each other. Okay, so that how do we manage the problem that let us say Tata Motors car is being charged here at the Mahindra, and what electric pricing they will give. Okay, so the pricing algorithms and all that has to be put on the cloud platform something, and some sort of blockchain-based smart agreements needed to be made, which will be automatic. Okay, smart blockchain-based agreements means there will be no third-party player. This is an algorithm which will determine whether the pricing constants given by different point operators, whether they are going to be sustainable or not. And they will need the information of the health of the battery, health of the car. Okay. So why it is required? Let us say one poor health battery is there, and you are someone is charging that one that particular car. So you may need more amount of energy to charge that one. Okay, so that kind of charging tariff, that person should be able to pay more, or should pay more, because the health of the battery has deteriorated. It's his fault, or it's his car's fault that it has not undergone repair or something. So that entire thing, the health of the battery, the health of the cars, all that needs to be somewhere stored, and according to that, some tariffs are required. So that is also a part of the digital twin. So this is something I put just for the one upcoming challenges of the wireless power transfer. In the wireless power transfer, basically there's a receiver coil and there's a transmitter coil, and they are going to transmit the power from receiver to transmitter. But whatever you have seen, like we can charge the mobile using some pads. With this, those are wireless power transfer. So they are below, all of them are below 1 or 2 kilowatt, hardly 3 kilowatt. Okay, usually they are 500, 600 watts, but still, if I'm being too hopeful, I can say it's below 200 and 300, 2 or 3 kilowatts. So let us have a look at of this circuitry. So there will be some coils, there will be inverters, and there will be rectifiers. Okay, and these systems will operate at a fixed frequency. The frequency will be the resonant frequency, and that will depend on the values of the inductance of the coils, majorly the inductance. Any coil which is operated at a frequency of 85 kilohertz or 100 kilohertz, as given by SAE 2954 standard, these are the frequencies in which we are going to operate the charging wireless power chargers. The inductances and the monetization, demonetization will take place. If you want to do an assessment of your charging infrastructure, in which wireless power transfer is also there, you need to be able to estimate the inductance values without using impedance analyzer. Okay, you cannot have 30 lakhs impedance analyzer stored everywhere. Yeah, so this is related with automatic navigation. Your electric vehicles digital twin is very much required for this one, because if you see the dynamic model of the electric vehicle, it needs multiple constants. Let us say the slip constant and the cornering stiffness of the car. And in the automated navigation, if these parameters are wrongly estimated, the automated navigation is never going to take place. Automated navigation right now may look irrelevant, but whether you like it or not, in next 10 years, it's going to come on the road everywhere, Europe and India alike. Okay, there will be special corridors made for this special navigation. And at that time, keeping track of the EVs, their parameters, is going to play a very important role. Definitely all the power is going to come from the battery, and multiple types of batteries are being worked out. Lithium ions are now, people are also trying to develop the sodium ion cell. Okay, because one of the major reasons is that this is 10 is missing here, by the way, 170 and 160 kilowatt. They will have higher energy density. Okay, and the risk of thermal runaway is lesser in the sodium cells. And the cycle, we don't know. It's in the research phase. We will have to look into that one. And the lithium ion cells here, at the lower temperature, their operability or their performance completely drops. But at the sodium ion cell, it can still operate at an efficiency lesser than 90%, somewhere close to 90%. It may not go above 90%, but still, as compared to the lithium ion cell, which is completely useless under the cold temperature, sodium ion is a big solution for that one. Other important components of this electric vehicle mobility is the battery management system. So we all know that battery packs are made by series and the parallel combination of different cells. Each cell can be of some small voltage, 4.2 volt or 3.3 volt or 2 volts also. And if you need to have, let us say, something like a 350 volt, and if you are using a 3.2 volts, then 150 by 3.2, you can imagine large amount of cells will be required to be connected in the series. Okay, if you require something like 400, 500 ampere hour, multiple of these series will be connected in the parallel stream. Now, one of the major problems in charging and discharging this one is that, let us say, you are charging them, and even if you take all the care in the world and try to develop exactly identical cells, there will be some runaways somewhere after use of 2 years or 3 years of the batteries, and some of the cells will undergo parametric drift. So what will happen? Some of them will hit the highest limit of the charging sooner as compared to the latter. Now, if that happens, you imagine what's going to happen. One of the cells, let us say, has hit the maximum charging limit. Okay, why? Because it has drifted as compared to the other cells. At that time, other cells, all the other cells are 10% still less. When their charging state of charge is at 90% only. And if there are 50 cells like that, so 10% you are losing in each of the cells just because one of the cell has hit the highest point. Okay, so that means this one single cell can limit quite measurable amount of power delivery capacity of the battery. So it will limit your range. The range and anxiety which is in the customer for a car, that's going to become more severe if that is not taken properly care. So for that, battery management systems are being developed. Already what are in the market, those are the passive battery management systems. Means you dissipate, if it is extra, you dissipate it at some resistance, or capacitive, where you can try to dump that extra charge to some other cell. Okay, but usually it will be charged, it will be dumped into the closer ones only. It is limited. Okay, by the designs like that, if you try to dump in any of the cell, the design which is requirement for that is going to be very cumbersome. So that is one of the limitations. Similarly, if a cell has hit the limit point, so if you're discharging your car is running on the road and one of the cell has hit the lowest point, and at that time still, let us say 10% charge is available in all of the other cells, and still you could have gone for other 50 kilometers and reached a charging station. But just because one of the cell has hit the lowest point, you can't do anything about it. Okay, so these are the problems. So a battery management system which can take care of all of these things. So one such solution we have proposed from our department, and we filed a patent for this one, in which each of the cell is connected. See here, what is the difference? Here, each of the cells are connected in a series. Here, each of the cells are not connected in a series. There is no connection between each of the cells. They are connected in the series via a bidirectional DC-DC converter. Okay, so this DC-DC converter can act as a boost, or they can act as a buck. And in this solution, if this cell has hit the lowest point, you can bypass them. Or since now we have a converter, you can charge them or discharge them at a lesser rate. So imagine a situation where all of you are discharging, and this is going to hit the lowest level at the first hand. We know this. Why we know? Because BMS keeps the track of all the cells charging and discharging limit. So in that particular case, we will discharge this particular cell at the lower rate. We will not take that much energy from this cell. We don't want to hit this cell the lowest point before the others. We could not have done this here. In this one, it was not possible to do this because all of them are connected in the series. But here we can do that because we have control over how much charge and discharge current we are going to take or away, put into this one, or we can take away from each of the cells. So this is one of the experimental prototype which we have developed and demonstrated, and we published the patent actually for this. So after I have discussed all of the major components, drives, motors, batteries, BMS, okay, now it's time to see how we can incorporate the sustainability. So this is the second part of my discussion. Before I move to the second part, if you have any question in between, you can go ahead and you can ask until this. Otherwise, I will move ahead. So next, in order to incorporate sustainability in the electric mobility, okay, what are the things which we need? So we need a modular design basically. Modular design, why you see modular design for the power converters, inverters, and these things, so that if I have to scale them up, scalability is a big issue actually. If you can scale the design, automatically scalability inherits the sustainability. Okay, so if they are modular, if not, you can easily add or remove the parts like converters and the batteries very easily. And yeah, so this is one IEEE standard which is designed for interoperability. So interoperability has been defined by IEEE 2030.5 and also by IEC 61850. Okay, in which the standard protocols has to be followed by all of the vendors. Okay, now let us say I have bought a EV Nexon and I want to, something has gone wrong, and at that time there is in the global market there is some shortage, because of which Tata is not able to provide some certain parts, but Mahindra is able to do so, or some other vendor is able to do so. So the design should be interoperable so that at that time this the other part can be put into that one. Definitely flexible control is required, so that if the operating conditions are going to change wildly in the electric vehicle, if you are running a car in Rajasthan, if you are running a car in the Himachal Pradesh or Uttarakhand, the temperatures are wildly different. That is going to affect your insulation, that is going to affect your battery life, that is going to affect your drive systems also, because all of the inverters, converters which are made of IGBT and MOSFET, they are temperature dependent. You cannot operate them at a very high temperature. Okay. So coming to this part, like I was discussing, once I showed you that all the data needs to be collected on the cloud. And so for that, IoT can be a very easy solution. Okay, because IoT devices are very cheap cost, are of very low cost. They are not SCADA-based systems. SCADA-based systems, you cannot put one SCADA in every car. It's not possible. But IoT-based data monitoring, or basically IoT-based system parameter monitoring, can be easily installed in all of the cars because they are very less costly. And all of this cost has to make the break-even point as soon as possible. Electric cars are usually costly than the, if in Nexon, if you can buy 9 lakhs to 10 lakhs, the gasoline one, I remember the previous one, the EV version of the same Nexon will charge you about 15 to 9, somewhere between 15 to 19 lakhs. Okay, even 19, I think more than 19 lakhs. So, so your saving of the power. So I should not have repeated repairing. That's going to incur recurring costs. I should not change the batteries immediately. Again, that's going to stop me from achieving the break-even point. Okay, and so these are the things which are very important for the sustainability. Okay, so yeah, so I actually discussed already. We want sustainable electric mobility because we would like to combat the climate change. That is the entire reason that again we are back to 1900s where we left off. We left off our electric vehicles in 1900, went for the gasoline. Totally, it was led by Henry Ford revolution of the gasoline-based engines, and now again we are back to the electric vehicles. Okay, so definitely we want the cost to be reduced. How the cost will be reduced? Because unlike your IC engines, it will not require multiple repairings and maintenance. Motors are very rugged as compared to the IC engines. Usually they will not fail, and if we have mechanisms to predict the upcoming failure, that will make it even last for longer. Okay, and definitely energy security is required. Means don't want to be dependent on the fossil fuel and the petroleum. So that is good. That's a good thing here. One can argue how much energy we are spending on the extraction of the lithium ion. So you can do. There's a calculation for that one. It's not about the energy we are spending on the extraction of the lithium ion, but the efficiency so through the efficiency of the gasoline-based engine is less than 50%. And the efficiency of this EV engines are more, EV cars are more than 90%. So by running the electric vehicles for the longer duration, we can meet the break-even point and we can beat the cost which is coming from the gasoline-based cars. So the question is, I want to run it for longer time. So how healthy is the car? How do I come to know? So I will have to find out the system parameters. All the system parameters are required. Okay. So let us have a look at the system parameters, basically. So we want to incorporate sustainability because we want it to be the fault tolerant, adaptive, prognostic. Before something happens, you should be able to diagnose it. Low mean time between the failure. Okay, emergency response, if that is also, it should be able to address the emergency response, and noise immunity is also there. So I expect that somewhere all of us have gone through some basic electronics, and those who are expert in the powertronics, they can definitely understand the importance of the high power capacitors. So I have taken this data sheet from one of the manufacturers, where 4700 microfarad is a capacitor which is being utilized as a DC link of the electric car. DC link of electric car means the DC link which is going to power the inverter, and the inverter is going to drive the wheels. If you see the tolerance, they have mentioned by themselves is plus minus 20%. Okay. So out of 47,000 microfarad, you can have a plus minus 20% up and down. So that much tolerance you have to manage. Now, if we talk about the inductance, it's a 47 microhenry inductance. The inductance also, so where we are going to face the inductance in the converter design, we are going to use L definitely. Okay, inductance is also there in the windings of the electric motors, and if you see, the changes are 20%. It may not look like much, fine. What it looks like fine. We can go for plus minus 20% tolerance. But now let us see what happens. So let us say if you're able to detect these values of inductance and capacitance, and after some time you are finding out that certain capacitance or inductance is going beyond this range. It has not failed yet. Just because if it crosses 20%, if it goes to 25% or 28%, that doesn't mean that inductance has stopped working. Similarly, the capacitor, if it crosses the range of plus minus 20%, doesn't mean the capacitor has stopped working. But going beyond this range is an indicator that something is wrong. Okay, and how do we come to know that? So that is about the digital twin. So here I have shown you, I have kept the discussion to a very basic minimal. So it's a DC-DC converter. It's a boost converter. Okay, when I showed this circuitry to one of in a discussion with the faculty, many people told means they could not recognize this one. If you see, this is nothing a simple boost converter which you probably read in the 4th semester or 5th semester in our BTech days. It's an inductor, it's a switch, it's a diode, it's a capacitor, and it's a resistance. Now, this RL is basically parasitic resistance. So any inductance will have its own parasitic resistance. Okay. Any diode will have a forward voltage drop, and it will also have an on-time resistance. So these are some things which you have not put deliberately. You are only putting inductor, you are not putting an RL. But by design, by the inherent properties of the inductor, these parasitic elements are present there. You can't do away with them. Forward voltage drop, you can't do away with that one. On time resistance of the diode, you can't avoid them. You are not putting it there, but by putting diode, you are actually putting it there. The switch will have a forward voltage switch drops. And what is this inductance doing here? So this inductance is basically called any MOSFET. Any MOSFET, if you see the three legs, MOSFETs are there, gate, drain, source. Those leads also have their own inductances. Okay, so this is called lead inductance. So these are also the parasitic parameters which are hidden there. We have not put them in the circuitry, but just by putting a MOSFET, we are putting these inductors and this forward voltage source here. Okay, this is basically forward voltage drop. Now let us say if you know that your forward voltage drop of an IGBT, or sorry, of a power MOSFET is 1.2 volt, and after some time you're finding out it has gone below 0.8 volt. That is a clear indication that this MOSFET is going to fail. And if you come to know this, you can suggest some sort of repairing and maintenance, because before the actual fault occurs, if this switch fails, the entire DC link will be shorted, a huge amount of fault which can actually affect the other parts of the system also. Before that occurs, a cascade of failures, you can actually stop them. Only problem is that we don't know this. Means once it is set in the car, it's in the car. Are you going to open the car and open the power converters and go with all your gadgets and equipments and measure this forward voltage drop? Not a practical solution. Definitely, it's not possible. It's ridiculous. Okay. Yeah. And this is where you can see here. It means so this was a boost converter from this direction, and this is basically, if you see here, two switches are there, and two switches means they will be able to operate in the both directions. Already by using one switch, we have put so many parasitic inductance unknowingly. Again, we are going to put one more switch because it has to be bidirectional. The braking energy we would like to store in the battery, and so again this has come. So after, if you do all of this analysis, what you can find out that the boost converter up to 0.7, this is also sort of not exactly linear, but if we can approximate it with the linear, we can say up to 0.7 or between 0.6 and 0.7, it's linear, and after that it drops. So if we remember the mathematical equation of the boost output of the boost converter, it is V in by 1 minus D. So if you keep going on increasing the duty cycle, actually I should have gone above. But after 0.7 itself, we are going down. So this is a very big non-linearity which is available there. Why it has come? If you model considering these all parasitic elements, you will find out that this is the fact. One can just put a program mathematical in the MATLAB and can do that, and can do this calculation. So just going back to connect these parts here, we have started to see that we would like, for sustainability, we would like to know when we are going to fail. In order to know when we are going to fail, we need to know the parameters, health of the system. Health of the system means how healthy is the car, means what are your system parameters. Okay. So yeah. So you are saying here, I was discussing about these values, right? The variation of these values. One example I showed you from the manufacturer data sheet. Now here I have shown you the probability of these variances. Right? This is voltage forward voltage across switch S1. Forward voltage drop means this is not the voltage which you are providing. This is the switch's inherent voltage, VSW1 and VSW2. So they can vary in between 1 volt to somewhere close to probably 2.5 volt. Okay, and so this much amount of variation is there. The RLF, that can also vary up to some extent. So these are the limits. This inductance. So inductance can vary from up to this range to this 2 nanohenry. So different. So this is for LSW2, LSW1, RSW2. So these ranges are definitely this RS here. What we are showing RLF that cannot go lesser than this one. Okay, these resistances. So these are in the milliohms actually. Means this is ohms, but if you see 0 ohm, 1 ohm, this value will be certain about 200 or 300 milliohms. Okay. So what about how it's going to affect actually? Now let me tell you one thing very clearly about these discussions. These are not going to affect your system in the steady state conditions. Mark my statement. These are not going to impact your systems on the steady state conditions. Reason, you have a age-old friend PI controller. You have an integral controller. That integral controller will sooner or later bring your system response to a steady state error, zero steady state error. We all know mathematically, final value theorem. If you apply in any, doesn't matter what order of the system you are having, sooner or later that is going to become zero. Thus, the error is going to become zero. Okay. But the failure doesn't occur at the steady state. The failures occur at the transients only. Okay. So if you look at this one, if you look at the steady state part here, so what is this actually? These are the voltage response and these are current responses. This is the lower one is the current response, the upper one is the voltage response. So at the steady state, you can see all the voltages are reaching the final value. No, almost no error. There's no error here. But if you look at the transient, the amount of dB by dt is huge here. The oscillations are huge in the voltage. The oscillations in the current are also huge. And these oscillations are plotted for two different values. You just look at the red one here. The initial two oscillations are almost similar. The red one is if the value is 0.9 ohm, the value of the parathetic resistance across inductance. If the value changes from 0.4 to 0.9, the red one, the oscillation is here like this. Okay. The blue one, if you can see, there is large amount of the oscillation. Okay, in the output voltage of the power converter. Okay, so only how much change occurred? 0.5 ohm. Only 0.5 ohms change has caused large amount of oscillation in the power converter, and this is where the switches have maximum chances of the failing. The devices can fail here. Okay, so that is the reason. That's why I told you nothing is going to go wrong if you talk about steady state, because PI controller is our very good friend. After some time, if you leave it long enough, it will bring down every steady state error to zero. Similarly, for the current response also, you can see there is a large amount of oscillations for one value of the inductance and lesser amount of oscillations at 0.9. So that means if your parameter has changed, your transient will also change, and that's going to affect the health of the system. And if you somehow can know that no, RLF has changed from 0.4 to 0.9, okay, that means something is going wrong in the inductor side. Why this will change? And some sort of prognostic actions can be taken place. To prove my point, even later, if you see the output response here as compared to maximum duty cycles. So let me show you one thing here. I don't know whether I have that other graph. Yeah, it is there. So I will show here. So here you can see, if you see the latter part, output voltage, this is the output voltage compared to different values of the resistances here, right? Different values of RLs from starting from 0 to 300. These are all milliohms. Okay, I forgot to mention here. These all are milliohms, 0 to 300 milliohms, and this is seconds. Okay, so if you see later on all and they for all the resistances, it has been plotted. Okay, so you can see there is a amount of thickness is here. Means your different output voltages you are obtaining, but at the latter stage you are obtaining only single output voltage. That output voltage is single. That means the steady state will reach for any value of the inductance. But if you see, some amount of thickness is here. I will show you in the next slides. It's very well shown here. Thickness means what? Multiple graphs are put for different, means you're getting multiple output voltages for different RLs. That is why here it has become thick. And this is the duty cycles. Just give me opportunity to explain this one. Now here you can see one. I have expanded this part. You can see this thickness of due to different input voltages here. Okay, so the transients, the transients are different here, but finally the output voltage is like a thin sheet. Okay, and here you can see this thin sheet, the same output has been obtained for different duty cycles because your system parameter has changed. I was not able to show it here because the change because of the RLF is not that much visible. But if I change in the input voltage variation will also be there. That change in the thickness is much larger. Now, if you have multiple such power converters which are needed to share this power at a common load, maybe this is the DC load, DC link for the inverter. Okay, and so you can implement a droop control sort of thing in the DC converter, which I think I will not explain here, but this is a well-known method for the power system. By using different slopes, you can have share of different currents. Okay, so what the point which I want to tell to you is that the SOC also drops with the temperature. If you see the graph of the SOC at the output voltage, if you see the output voltage here drops for different temperatures at the same amount of percentage. You can pick up any percentage of the SOC, 70% or 80%, for any single one of them, the voltage will drop. Okay, so input voltage drop is also one of the major reasons. That is, in the car, as I told you, the car is going to face wide range of operating conditions, particularly in the input voltages. Okay, so what is the solution for this one? So real-time system awareness. Real-time system awareness is the solution for this one. If we can know this this RLs, sorry, where is this? Yeah, so this RLs, LSW, BSW1, BSW2, without actually opening the car and measuring it, because that is not practical. Once the car has been sold, you will not be allowed to do so. So how we can, or the companies, how they can keep track of them when the car is running? Car is not going to come to the service station every day. You will be taking the car to the service station 6 months or maybe 1 year once, something like that. And in between, if there's a drift has occurred, already the damage is done. So so the real-time system awareness is the solution. That leads to the parameter estimation. Okay, which brings me to the third part. So before I move to the third part, if you have any question or query, you can ask till now.
Participants may ask if they have any doubts related to what has been discussed till now. So I think we can proceed to the third part.
Okay, so so we will proceed. Deep sir, I have time till 9:30, or what is the time I am having?
Sir, 9 p.m. sir.
Okay, fine. I thought it was
Okay,
9:30.
Oh, okay, sir.
Okay, so coming to the parameter estimation, we have seen that digital twin is nothing. Okay, let me clarify. What is the difference between digital twin and real-time parameter estimation? If you see, I will just, I will go here and I will show. Is there anyone commenting so you can discuss? Okay, so here what you can see here, that actually in a digital twin there is something called federation layer. Okay, so the federation layer, the difference between the digital twin and the real-time parameter estimation is that in the real-time parameter estimation, you estimate the parameter in using some real-time controller or some algorithm or using some sort of data acquisition system and putting in your Kalman filter or observer-based algorithms, and then you use it for your control algorithm. And after it has been used, when the next parameter is again being estimated, that data will be lost. Now you can argue, no, I can store it. Fine, you can store it, but for how long? Digital twin is going to exist for the entire life cycle of the car, for entire 40-50 years. All parameters will be stored in the federation layer, which is given by IEEE standard P288.3, which will enable you to keep a track of the drift in the parameters of the any parameters. I have discussed only the electrical ones, but also the mechanical ones. Mechanical parameters also can be taken care of. That is, and definitely cloud gives you infinite resources for almost infinite resources. You can subscribe to their E2C instances, which is basically compute instances. You can get allocated GPUs. You can run your machine learning algorithms, and you can find out any sort of features from the data which you are getting. It's basically a gold mine for AI ML people. Digital twin is a gold mine. You suffer for the data in the electrical engineering. But if you have a digital twin of a car, last 10 years data, apply your AI ML algorithm there, and we can have you can predict about the health. That means predicting the sustainability. That is the difference between digital twin and the parameter estimation. So parameter estimation, you have seen that equivalent series resistance. ESR is the equivalent series resistance of the inductor. Stray inductances like the inductance, I talked about the lead inductances in the MOSFET, and the diode voltage drops, they vary with the temperature, switching frequency, and device aging. Okay, so a dynamic estimation approach is required. Once you have estimated the parameter and then you forget about it, that's not going to work. You have to estimate them on regular intervals, store the data for entire life cycle of the product, and then you can basically that can be a good solution for sustainability. So digital, so it's a virtual real-time mirror of a physical system. So a physical system is a physical system which is existing in the real world, and digital twin is basically a high fidelity mathematical model. Okay, remember how much depth we went into just for the power converter. In the boost converter, where usually when we are thinking, we are only designing it for inductor, MOSFET, and capacitor. But just now I showed you that an inductor is having resistance, MOSFET is having two inductances, one forward voltage drop, and diode is having forward voltage drop, and on-time resistances. They are not just a single components. Okay, so if you do such kind of high mathematical model and you store them, and you can use them for the predictive maintenances. So these are the layers. Okay, so so this is this layer is basically connected with the physical world. Okay, where all the data is going to come here, and from here through the cyber physical system, it's going to get mathematical model into the mathematical model of this one. And then you do the modeling and simulation. You compare your results with the physical systems results, whether they are same or not. Correct your model, and if it is fine, then that means you have the correct information of all the parameters, and then you can have some application layer. Okay, this is the framework. So I will just at first I will come here, then I will go back and I will explain this part. So here you see, this is the basically physical space, the hardware of the power converter. Okay, and this is the cyberspace. In cyberspace, what is there? I have put one state space model here. Okay, this state space model is the high fidelity mathematical model considering all possible non-linearities and non-idealities in the power converters, and all the data like all the sensor data are being propagated through IoT to a storage in the cloud. Okay, and again, I will come here. I know that I'm showing this part here. Just a minute. So this part, after some time again, I will come back here. So through the network interface, which is basically IoT, we are storing this data. We are computing this mathematical model, and through this mathematical model, all the state parameters we are computing, and that parameters are actually means you are computing what should be the output, what should be the inductor current. Sample by sample, you are computing this, and then you are comparing this with what has been measured. If it is correct, that means your model is correct. If your model is correct, then no need to proceed here. Okay. If it is below some error criteria, okay, you can directly basically store this estimated parameters, and you can provide this to the controller which is there on the car, on board on the car, or on board vehicle, or on board on any system. Okay, but if the error is not less, that means your model is incorrect. Incorrect means the parameters which you are using in the model is incorrect. So you find out their errors, means there is their change of the rate of errors with respect to change in the parasitic values. Okay, because ultimately you are so I will just explain this part here, and then what is happening is you are seeing this, these features are there, switch average voltage, inductor average voltage, harmonics. All these parameters we are feeding to an ANN algorithm, which is basically RNN, recurrent neural network, LSTM, long short-term memory based AIML. I could not have done this on an onboard microcontroller, but I am able to do this on a cloud because it is having very good computational resources. Is it required for a single DC-DC converter? No, not at all. Why I will pay another 10,000, 20,000 rupees just to keep my converter ready? But is it required for a car? Yes, the car is 19 lakhs. So if just by spending another 20, 30,000 rupees, the company can keep track of the health of the car, and if they can tell you that your car health is deteriorating, you need to, and it's not only for one car. You can do it for hundreds of the cars. Okay, so yes, then it is useful. So after the parameters has been found out, these parameters are being again fed to the mathematical model. If the model is incorrect, again the same loop will be continuing until the error has become 0. And the error becoming 0 means what? Your mathematical model is correct. Now, one catch is here. This is for homomorphic transformation. That means we are considering that there is one-to-one relation between the parameters and the output. That means there is no other combination of these parameters which will give you the same set of output voltage and the current. Okay, that means accidentally it is not possible. The entire approach of LSTM or ANN is based on homomorphic transformation, linear transformation. Okay, that there's one-to-one correspondence. If it is not there, then definitely it's not going to work. But till now, it is not proven. So coming to this, you can see that this entire computation, mathematical model, parameter estimation is happening at the cyberspace or in the cloud platform, where this is a physical space. However, the data of the parameters are being percolated to this network interface, which is giving the data to the converter itself for controller, means the hardware containing converter with microcontroller. Okay, so now if you can understand that what is the model parameter, if you are implementing a model predictive controller, it will be a holy grail for MPC, because every time your model is getting updated. Okay, now this updation, how much time it needs to take this updation? See, the model parameters are not going to change every millisecond. The resistances or the forward voltage drops, they will change over time, after some days, after some weeks maybe. Okay, in some extreme cases, maybe few hours. After a few hours, they will change. But so the parameter estimation doesn't need to compute this every millisecond, or that kind of requirement is not there. It can wait. It can easily do its own work for few minutes and update it to the MPC or your controller to change its parameter controller gains after some time. So high fidelity sub-cycle simulations are required. Sub-cycle simulations means your system has given you some data, and system has then departed from that data, and after that you are computing that what parameters could have caused this result. And definitely for any backpropagation algorithm, you have this gradient propagation. Yeah. So now see, this is physics informed algorithm. Okay. So yeah. So this is a physics based simulation. This is not data driven. That means I am not telling you that you need to have quite large amount of data to train your ANN algorithm here. Okay. So you get some value. Your error, any ANN works with the computation of the loss function. Most of us know. The loss function is computed based upon the error between the target and error at the actual output of the neural network. The target is where you need the data, training data set and target data set, right? But your target is given by the actual system, your measured system, right? This is the target which you need to follow. And if these parameters, there's no target for these parameters because these parameters are being fed to the mathematical model. And then whatever the measured computed value is computed against the measured value, and that is causing your cost function or loss function, popularly known in the AI/ML community. Okay, and that you are trying to optimize or minimize using backpropagation algorithm for each of the PJs. That PJs means parameter of parasitic parameter, jth parasitic parameters. Okay, so in this kind of physics informed information, you don't need large amount of data set. Okay, so this is IoT based communication. You will need this definitely for a digital twin, for coordinated charging, for health monitoring of electronics and all. This is IEEE 2413 architecture for the IoT. Okay, so in this you need to have a sensing device, you need to have a communication, and you should be able to do something with that data. This is basically IoT interface. So one more thing to the students, if you are thinking that Node MCU, ESP32 or ESP8266 are the IoT devices, definitely they are the IoT devices. But any IoT device, take a microcontroller, put a Wi-Fi module, and connect it with some server, that becomes your IoT. Okay. So any IoT which is having these three parts, they are basically IoT. You can have even GSM GPRS based communication. You take the data and you through cellular tower, you are sending it to somewhere, to some server. So I explained this part. I will skip this. This is where I have just shown that multiple sensors are there, and your RPI, for the practical point of view, your RPI can act as a server. Okay. So I discussed this part, that how digital twin, this I've discussed already. Yeah, so I put this just to remind you that what is happening here on the cloud platform. On the cloud platform, you can see all the variables, all the measured data are coming. You are doing a state estimation. Okay, you are minimizing it using, you can also minimize it using some sort of evolutionary algorithm. Okay, and after minimization, you are feeding all that state variables to your system, back to the system. So how does it work actually? This backpropagation algorithm you can see here. So this is known to all of you. Input layers is there, hidden layers are there, activation function is there, and through this activation function we are getting the values of the parasitic parameters. Okay. Now in this one, now in the conventional neural network, what we would have done, these parasitic parameter would have been compared against a target data set. In this one, what we are doing, we are feeding this to the mathematical model, high fidelity mathematical model, and that is giving us switch current, inductor current, output voltage, and we are comparing this with the measured value. From where did we get the measured value? Through the IoT interfaces. Okay, and we computed the error, and this error through the chain rule has been the rate of the change of the error with the rate of change in the weight for each of the units in the layer has been computed, and then you propagate it back to the input layer. So this is basically how it actually works. Now you can definitely you can replace these neural networks with RNN or LSTM or GRU. That is a different thing, but that is the info. I wanted to make a point that what is the difference between the conventional neural network and the physics informed neural network. This is the difference made. So definitely, yeah, for this converter actually. One more thing, mostly the power electronics people will tend, means I used to do that. I used to develop a averaged state space model. I think all of you, all of the power electronics people or power converter, anyone who has ever developed a power converter model have heard of the average state space model. That's not going to work for this kind of systems. So you need to have separate dynamics for the on state and separate dynamics for the off state. Okay. And that so for time to time you will need to compare them. So on state dynamics you see two equations, A on and A off. In averaged, what happens is single A, single B, and single C is single D. A, B, C, D matrices are there. But here a separate matrix for A, separate matrix for B, and we are not going to average them out. If you do that, then then you will not get this thing. I was showing in those transients, those will be also averaged out. Then the entire point on which our discussion is based, the parameter estimation, that information will be lost. Okay, so I have just shown you this is A on and A off, these two different things. They have not been modeled. So piecewise linear means we are considering doing the on time model separately and the off time separately. Okay, and this is the difference. You see the average, the actual piecewise model is giving you this kind of transients here, this kind of transients here. But in the average model, you are not getting any transient. It is seeming like system is working very well. So I discussed this part. This is where neural network parameter mappings are happening. Okay, the p values is basically the activation function and the bias which is coming from there. Y model, the model output error. So error is basically this output which you are getting after feeding into the mathematical model, the parametric values against the y measured, subtract them, norm, and you know, because basically we want to go towards the root mean square error, and using that that part here, the gradient weights are being updated. So initially, if you see the final formula here, it is W ji old minus eta, that is the learning coefficient, delta jr, which is the previous delta jr, right, and del w ji compared with this. What is this gr actually? This gr is this one. Okay, this is the del gr. So basically, we are comparing how the error is changing with respect to the change in the weights, and we are feeding it back. This is where we made the major difference, or not we, means the digital twin makes a major difference. So we did some experimental work on that one using these parameters. Okay, and so here you can see initially when we wanted to observe the parameter, there was wild variation. This is estimated parameters. These are totally wrong actually. Initially we are getting a very wrong value, and in the last the error was also reducing that error. In the last we got, so here the error has become very small. Error between the measured inductor value, inductor current value, and the computed inductor current value is very small. And at that time, the value which we have got R1 and all this, these we are considering them to be the actual parasitic values. Now you can say, have you measured it? Means did you measure it? Yes, that analysis we have done. After measuring this, they were very much similar with the estimated ones. Okay, and this we have done for the different duty cycle. This also breaks another myth that the parasitic values of the converters, inverters, motors, batteries, they are going to remain fixed for the same duty cycle, for all duty cycle. No, for 40% duty cycle they are different. For 50% duty cycle these values are different. For 60% duty cycle they are different, and that is why your error is also getting reduced here. That means for the power converter people, this can act as a new information that if you have different duty cycle, actually the values of these parasitic values also vary as per the duty cycle also. This is the table. Same thing, but for different duty cycles, they are having different values. Okay. So, so digital twin tracks your parasitic variations, and they are going to happen, and they are the indicators before the fault occurs. If you can detect them, you can have sustainable solutions for the electric vehicle technology. Okay. Yes, that definitely we have to consider even I told high fidelity models. So actually there are multiple capacitors which we have omitted in this analysis. One can do that analysis. If you do that, you will be able to publish a paper on that one if you are incorporating high order dynamics. That will be even more accurate. Okay. So yeah. So with this, I think I would like to conclude. If you have any question, you can go ahead.
Participants, the session is now open for. If anybody has any doubt, may please ask.
Good evening, sir.
Sir, good evening, sir. Hello.
Am I audible? Yes, yes, good evening.
Sir, is digital twin technology is possible without hardware, sir? It's complete simulations.
No, it is not possible because why you are doing a digital twin? Because there is a physical system. If there is a physical system, then only you need digital twin, right? So if there is no physical system, then why I will go for the digital twin? So you need to have a physical system whose digital twin you are going to develop.
Okay. So sir, its complete simulation is not based on only MATLAB. So other platform would be needed. IoT enabled AI or machine learning based platform.
It's a multidisciplinary approach. For digital twin, you will need IoT, cloud, then MATLAB based solutions, simulations. Actually, you see, this is I showed you just a minute. Is that?
Good evening, sir. Sir, yes, as you talking about the IoT digital twin interface.
Yeah.
Sir, my question is, if the IoT sensor feeding the digital twin wrong data, how does
I'm not getting. Can you repeat again? I could not get you actually.
Does the twin know what's real?
Can you type your question in the chat box? Or Deep sir, if you are getting the question, can you tell me? I'm not able to
listen.
The IoT
sensor feeding the digital twin, how does the twin know what's real?
The question is if the digital twin is if the twin is digital, how does it know what is real?
Yes, sure.
Okay. We know. See, the digital twin is the replica of the physical system. The digital twin exists in a cyberspace. Okay. Now, how do we know? I think your question is how do we know it's correct? It's the correct replica of the physical system. Okay. So it's correct replica that is known if the root mean square error is appreciably low. If it is low, that means the measured value of your car's motor or inverter or the battery is almost same as the data given by the digital twins batteries output voltage current or the inverter's output voltage current. If these values are so much same that the error between them is appreciably low or significantly low, then you can say that digital twin is correct.
Okay, sir. Thank you, sir.
And by the way, this coding, this programming was totally done on the cloud, on the Python actually. no MATLAB was involved, because I cannot install a costly software like a MATLAB on Google Colab. They will charge me heavily. So that is the reason it was entirely done using differential equations on the E2C instance of cloud. So if someday if we have some physical means the one-to-one, I mean the physical classes, then workshop kind of things, then I will try to set up one lab session for this one, where we will run actual motor, and we will show what RPMs are being shown by the digital twin.
Sir, is there any complete simulation and hardware results is available for digital twin for any your proposed approach, sir?
Available, multiple people have developed for digital twins for multiple systems, for multiple designs. Yes, in IEEE, multiple papers are already available on this one.
Okay.
I think
Hello,
there
sir.
are no more.
Hello, sir.
The other,
I have also one question.
Yes.
Regarding the skill sets needed for digital twin, sir. The rise of the digital twin demands a new kind of professional, sir, beyond the data science, AI, ML, and sir, what are the skill sets that need to be teach in the universities or companies need to be prioritizing to build the next generation workforce, sir, for digital twins? Like,
Basically, I will say mathematical modeling and the coding, particularly
okay, sir.
cloud-based coding.
Okay,
Three things will be required here. Mathematical modeling is, without mathematical modeling, this will not work. Number one is mathematical modeling, and
okay, sir.
second is coding. Coding skill will be required definitely. And third thing is how to how to configure the server on the cloud from this using
Okay,
this
sir.
data. Okay,
Okay,
if
sir.
these three things are done, then definitely this is good.
Okay, sir. Thank you, sir.
I think, sir, there are no more questions from participants.
Yes. Yeah.
Thank you, sir. I think we can wind up this session now.
Okay. Yeah. Welcome.
Thank you, sir, for the informative session covering a very wide spectrum of detailed information and um, research, open research avenues, details about electric vehicle, the charging infrastructure, and the basics and mathematical analysis, modeling, detailing of digital twin technology, sustainable electric mobility. I hope in future we can seek your guidance and some more sessions in our possible future workshops and FDPs also.
Yes. Yes. Sure.
Because I
Definitely.
think this session was not enough for many things, because the last part of digital twin has to be completed very quickly. Not going
Yeah,
into
I
detailed
realize that
discussions.
part. Yeah, if in the lab at least two or three sessions will be required in the lab to completely configure digital twin of any system. So
Okay,
that
sir.
is required.
Okay, sir. Okay. So thank you very much, sir, for accepting our invitation and giving such a informative and detailed session.
Yeah, welcome. Welcome. Actually, thank you for giving me the opportunity to discuss these research topics with a wide audience.
Okay, sir. So as per the practice that we are following since yesterday, I would request all participants to please switch on the camera just for a few minutes so that we can capture this moment with our resource person. And it is a request, sir, please kindly stop the sharing of the PPT.
Sharing. It is stopped.
Yes, sir. Yes. So just few minutes. I will take a few screenshots. Thank you very much, sir. And thank you all participants for switching on the camera for the screenshot.
Thank you, sir.
Thank you, sir.
Thank you,
sir.
Aftab, sir.
Thank you so much,
Thank
Deepak,
you
sir.
again.
Sir, I'm leaving.
Thank
Thank
you
you,
very
sir.
much, sir. Thank you, sir.
Dear
Thank you, sir.
participants, we will again meet tomorrow at the same time, 6 p.m. This first session will start in 6 p.m. And just like today, the second session will commence at 7:30 p.m. The session-wise feedback, the link for the session-wise feedback of the sessions of yesterday and today will be shared by tomorrow. So you have to
Okay,
give
sir.
separate feedbacks for each session, session 1, session 2 of day 1 and session 1 and session 2 of day 2. So you will have to fill 4 feedback forms, and subsequently we will share the links of all the upcoming session for session wise feedback. Thank you. Good night.
Good night, sir.
Thank
Okay.
you. Thank you. Thank
Thank
you.
you so
Good
much.
night, sir. There is a request that you please send it in the group also, sir.
Yeah, sure. I will email also, and I will share on the WhatsApp group also.
Thank you, sir. Thank you very much, sir.
Thank you very
Thank you
much.
for the
Thank you
cooperation.
for
Thank you.
participating.
Bye.
Thank you, sir.
Thank you.
Okay.
Good night.
Okay, sir. Good night.